So in our equation's goal, we're trying to take an equation and rearrange it in such a way as to get the variable in that equation by itself on one side. At the beginner level, we're just mostly trying to implement a strategy to solve an equation that has variables on both sides. Actually, let me dial that back. Let's not worry about variables on both sides at the beginner level. Let's just say that at the beginner level, this is to solve an equation by reversing the order of operations. In other words, using not PEMDAS, but SADMEP. The order of operations reversed. So here's an example. Suppose I want to solve the equation for x, and the equation is, I don't know, 17 minus 3x is equal to, how about 29? Yeah, let's do that. 17 minus 3x is equal to 29. So how do we do it? How are we going to get the x in this equation by itself on one side to discover the solution? And I'm choosing to subtract 17 here because why? How come I want to do that first?
Because it's going to isolate the one with the variable by itself.
Right. So I want to focus on the 17 because it's the thing that's most closely attached to the x. But I'm doing the subtraction before I worry about the negative 3 that's right here because we're using the reverse order of operations. That operation which we undo first is the operation that would have been done last when we evaluate the expression. Right? We're unwrapping the package in the reverse order in which the package was wrapped. So subtracting before worrying about that negative 3, which is multiplying the x. 29 minus 17. 12. And what's my last step to get that x alone?
Divide by negative 3.
Divide by negative 3, because negative 3 is multiplying the x. If we divide by negative 3, we will have unwrapped the x from that multiplication. What's 12 divided by negative 3? Negative 4. Great. So at the beginner level, what we're really doing is we're kind of working on the end game in solving an equation. Solving an equation using the reverse order of operations is kind of the last process in our sort of broader strategy for how we solve equations. Anytime we get to an equation which is completely simplified in such a way that my variable is only on one side, and there are no exponents, there's only multiplication and addition and subtraction and division, then the reverse order of operations is our strategy from there. So this gets us, like, starting in the red zone, starting with the ball on the 20 and running it into the end zone, right? So the next couple of things deal with what to do to get us to the red zone, right? How do we get to the stage where we can use the reverse order of operations when we have other issues involved in our equation? And so we brought in a couple of issues at the intermediate level. At the intermediate level, we also have equations with variable on both sides. So that was one extra complication. And with some fractional coefficients. So we want to add kind of both of these things into the mix at the intermediate level. Let's start with just an example with a variable on both sides. So we can kind of tackle these two issues separately if we can. So as an example of the former type, let's suppose that I want to solve this equation for y. Negative 1 minus 2y rather, is equal to 3y plus 9. So now my y is living on both sides of this equation. How should I deal with that? First thing I need is to get that y to be only on one side. Otherwise, there's going to be no way for us to get it isolated and solve for it. So how do I get it so that all my y's are on one side? Yeah, when we think about what happens, we think of it as a moving process, right? Just move this from the right to the left. But what's the arithmetic behind how we move it? Yeah, so what I want to do is I want to subtract it. Right? If I subtract 3y from the right side of my equation, then 3y will no longer be on the right side of my equation. But then if I do it on one side, I've got to do it on the other side also. So when we move terms from one side to the other, it's always a process of subtraction or addition, however you prefer to look at it. So now on the new right side of my equation, I only have 9. And the new left side of my equation is going to have -1, but how many y's am I going to have?
5y.
Yeah. -2 subtract 3 is going to turn into -5y. Well, great. So now that that step is done, we're looking at a problem that looks an awful lot like our beginner level, right? My variable's only on one side. All the algebra is simplified. We have mixed arithmetic. We have multiplication and addition. So how do I unwrap this y?
Add 1 to both sides.
Yeah, reverse the order of operations by starting to add 1 to both sides. That's going to give me, on the left-hand side, -5y. On the right-hand side, 9 plus 1. And finally, dividing by -5 to give me y equals -2. So that's an example that illustrates how we handle the situation of having a variable on both sides of the equation. Our priority is to get the variable to be only on one side by subtracting it, subtracting an appropriate variable term from both sides. And so that's how we handled that eventuality. Sneak that off to the side here. How do we handle an equation that has a whole bunch of fractions in it? So here comes one. Solve for v. And then I'm going to write my equation, let's say 2/3 v minus 1/3 is equal to 1/2 v plus 4. So there's an equation that both has variable on both sides and it has a bunch of fractions cluttering up the works. So what's a step that I can take that can deal with my fraction issue? The most underrated technique is to get rid of all of our fractions in one fell swoop, to turn them all into whole numbers. And once they're all whole numbers, the problem looks an awful lot like this one that we just solved pretty confidently because we only had to do whole number arithmetic to solve it. So how do we turn an equation with fractions in it into an equation without fractions in it? Yeah, there's the idea. What I want is I want to multiply both sides of my equation by a number. And remember, it needs to be the same number we multiplied by on both sides. But that number should have the power to cancel out the denominators of all the fractions in this equation. So it needs to have enough power, enough juice to cancel out the 3's on the left-hand side of the denominator, and also to cancel out the 2 in the denominator on the right. So what's a number that can both cancel the 3's and cancel the 2's at the same time? I'm looking for a number which is both a multiple of 3, so it can cancel the 3's, and a multiple of 2, so it can cancel the 2's. In other words, what we need is a common multiple of all the denominators involved. And 6 happens to be not only a common multiple, but it turns out that it's the least common multiple of 3 and 2. So this is the technique that we call clearing denominators. Right? And I took the liberty here of writing 6 as 6 over 1, just to remind us that that's what it is. So that the only fraction arithmetic that we have to do now is to multiply some fractions. That's good news, because multiplying turns out to be the most straightforward operation we can do with fractions. We take them as they are, no common denominators, and we just multiply straight across. Right? So now we just need to do that multiplication, that straight across multiplication, 4 times. Twice on the left-hand side, and twice on the right-hand side. How do I do 6 over 1 times 2/3? We could think of it as just going straight across. You're getting 12 on the top and 4 on the bottom. And then 12 over 4 turns into, oh, it's not 4, I'm sorry. 12 on the top and 3 on the bottom, which then turns into 4. Another way to think about it, this 2 is underrated, is that we can trade places with this 1 and this 3. In other words, I could rewrite this as 6 over 3 times 2 over 1. And that's kind of nice, because now each of these two fractions itself represents a whole number. What's 6 over 3?
2.
And And 2 over 1? 2. And 2 times 2 is 4. That's the way that I prefer to do it, because then, again, I'm trying to do as much arithmetic with whole numbers as possible and try to avoid as much fraction arithmetic as possible. That 4 has a v on it. Then I'll do 6 over 1 times 1 over 3, which, again, if I transpose the two denominators, just turn them around, I can treat it as 6 over 3 times 1 over 1. And 6 over 3 is 2. 1 over 1 is 1. And 2 times 1 is 2. So that dispatches with the fractions on the left side of this equation. All we have left to do is do the same thing on the right. 6 over 1 times 1 over 2. What do I get there? Same as 1/2 times 6. 3. And then 4 times 6 over 1. That's just 4 times 6. Those are whole numbers to begin with. So after that one step of clearing denominators, now we have no fractions left at all. And we're right back to the situation that we had here, where in order to solve this equation, I should get all the variables to one side by subtracting. So we'll subtract 3v from both sides of the equation. That's going to leave me with 1v minus 2 is equal to 24. And then adding 2 to both sides, we've gotten the v by itself. v equals 26. So clearing denominators, even though it's not the only way to solve these problems, it is, in most cases, the most straightforward way, because it avoids, to the extent possible, having to do fraction arithmetic. And that is always a good plan, because fraction arithmetic is rife with potential for making mistakes. Our advanced level skill is to implement these skills, so same skills that we've already had here, but to implement them in a case where our solution is not necessarily a number. So in all the examples we've seen so far, our solutions, our variables, come out to be numbers like -4 or -2 or 26. I just happen to choose examples where those are all whole numbers, but that doesn't always have to happen, right? Our answers could be fractions. But what we'd like to do is to use this not necessarily to solve for a solution which is a number, but to solve for one variable in terms of the others. So if I have more than one variable in my equation, how do I solve for the value of one of them in terms of other variables? So this is our summit level skill for goal number 2. So here's an example. I want to solve the following equation for f. And my equation is c equals 5 over 9 times f minus 32, where the latter is in parentheses. So here's an equation. But the deal with this equation is that it has more than one variable in it. It has a c and it has an f. Right? And so the question is, how do I rearrange this equation to get the f by itself? And when I do that, I'm going to expect that if I were to get the f by itself on one side, this c is not going to go away. It's going to be somewhere else on the other side. I pulled this equation from the equation in science for converting Fahrenheit degrees measurement to Celsius degrees measurement. Right? So the c represents the Celsius temperature, the f represents its corresponding Fahrenheit temperature. So this equation would be useful for us if we knew what the Fahrenheit temperature was. We could just plug it in on this side and it would spit out the Celsius version. But if I knew it the other way around, if I knew what Celsius was and I wanted to find Fahrenheit, I would have to do some algebra to use this equation. Right? If I plug in a number on the left side and then try to solve for f on the right side, it would take me some doing. So what we'd like to do is to rearrange this equation to get the f by itself so that we could use that equation more simply to convert from Celsius to Fahrenheit. So how do we do it? How am I going to get this f by itself in this equation? So the key thing here really is to suspend disbelief for a minute and treat this equation like you would treat any equation. let's imagine for a second that this c were not a c. Let's suppose that it were just a number. I don't know, 20 or something, right? If this were just a number on the left side instead of a c, then we would proceed with this equation just like any other type of equation that we were solving, and we would start by simplifying both sides, right? That's one way, is to multiply the 5/9 into both terms of this equation, and then go forward from there. Actually, there's another possible way to do this in view of SADMEP. Right? We actually have parentheses in this equation, and SADMEP, the reverse order of operations, tells us we should actually start from the outside of the parentheses and try to work our way in. So is there anything that I can do in this equation to deal with this piece, this 5/9 that's on the outside of the parentheses? Can I get rid of it somehow? Joe? So a way to approach this equation to get rid of the 5/9 right away and work from the outside of the parentheses in, according to SADMEP, is to divide both sides by 9/5. I'm going to treat this as though it's a number over here for a second, just to illustrate my point. So I'm going to treat this like it's a 20 instead of a variable c. And I'll start by dividing both sides by 5/9. Which is the same thing as multiplying by 9/5. So that's how I'm going to write it over here on this side. 9/5 times 20. And when I divide by 5/9, that 5/9 is going to go away. 9/5 times 20. Anyone see a quick way to do that?
Simplify the 5 into 20.
Yeah, exactly. So the way that I see that usually, remember, is transpose these two denominators, flip the 5 and the 1. So the 5 goes underneath the 20. What's 20 over 5? 4. And so I get 9 times 4. And that's going to be 36. So 36 is equal to f minus 32. And then how do I get the f by itself? Just add 32. And so I'm going to end up here with 68 equals F. So we just found out that 20 degrees Celsius is equivalent to 68 degrees Fahrenheit. Room temperature-ish. Comfortable room temperature for me, because I tend to run warm. Yeah?
Where'd you get
I got the 20 to start this process. I cooked it up for the purposes of this example to show us what the algebra would look like if we only had one variable, if we only had the F, and we didn't also have the C. So the good news is that if the 20 were still just the variable c that we started with, the whole process is still the same. Right? That we would still, so let me go back to where we were in the beginning with this, 5/9 times f minus 32. We would still have started by dividing by 5/9 on both sides, which is the same thing as multiplying by 9/5. Right? So here we would have 9/5 c. And afterwards, we would have then had f minus 32 on this right-hand side of the equation, which we would have handled by adding 32 to both sides. Because that's going to cancel the minus 32 on the right. But I also have to do it on the left. And so a bunch of algebra would pile up on the left-hand side that now we can't simplify in the way that we could simplify it when c had a specific value, 20. Right? But now we've done it, right? We've done the work of rearranging this equation to get the f by itself. It didn't require us learning any new strategies for algebra. We just had to follow our same instincts for how to solve this equation, how to get the f by itself. The difference is that instead of being able to do arithmetic like we could when this was 9/5 times 20 and make it simpler, now it just has to remain 9/5 times c. And when I add 32 to it, because that's not a like term, right, we can't do anything to make that simpler either, and so our final answer is just 9/5 c plus 32. So the good news is that it's all the same strategy that we implement when we're solving an equation that only has a single variable. It's the same process of reversing the order of operations. And the only difference is that we just have to suspend a little bit of disbelief and trust our instincts, trust our work, trust our algebra, to just carry the other variable, or possibly variables, forward with the algebra as we do it at every step. So the good news about this to a scientist is that now I have a nice equation that I can plug in Celsius into, and then it spits out Fahrenheit, which is the opposite of what the original equation did for us. And especially in the sciences, this is a strategy that you end up having to use a lot, because you get handed a lot of equations, or you discover you derive a lot of equations that relate various scientific quantities together. But the way in which they're given to you is not always the best format in which to use them. And rearranging an equation to make the variable that you care about the subject is a way to then make that equation more useful to you, so that you front load all the algebra, and then to use it, all you have to do is plug and chug with arithmetic.